one last concept we have is effect of dopant concentration. So this is very simple. So ED is the average energy level of the donor atoms, let's say in this case phosphorus atoms, right? So what this slide and this picture tells us is, as you increase the number of dopant atoms or impurity atoms in the semiconductor, the average energy level becomes broader. Instead of being one particular value, let's say initially I had 5 dopant atoms in this piece of semiconductor, and my average energy was 0.5 electron volts. I'm just giving you a rough example. So when I make it 20 atoms, the average energy, instead of being one value, it becomes a range. It becomes 0 to 0.5 electron volts. And when that 20 atoms becomes 100 atoms, the range becomes even broader. From 0 to 0.5, it becomes 0 to 1 or 0 to 1.5, something like that. So as I increase the concentration of impurity atoms or donor atoms, the average energy changes from one energy value to a range of values. So the average energy of all the donor atoms or electrons put together lies somewhere between 0 and 0.5 electron volts, or 0 and 1.5 electron volts, like that. So instead of being one particular value, it becomes a spectrum. And because of that, the Fermi level starts getting pushed up, because the Fermi level ideally has to be the midpoint between EC and ED. So as ED becomes a broader and broader spectrum, EF rises higher. If ED becomes a very broad spectrum, the Fermi level can even be greater than the EC or the conduction band energy level.